And it's focused on the board, on the code? Okay, it's viewable. Excellent. All right, so this is the third lecture of problem solving. Today is a fun topic. It's on computer coding. This is one of the most useful skills you can have. And so the problem we're doing today is we're starting off with the cookie problem. So I will open up just so. Okay, so just, so we're all on the same page. Cookie problem. We have C cookies identical, P people distinct. How many ways to divide cookies among people? Now, when you look at this, there are some potential implicit assumptions. What are the implicit assumptions? There's one really big one. Yes?
Like at least the cookies should be integral.
So it should be integral numbers of cookies. And you could actually talk about, well, what would you do if you had half a cookie? And this is a very interesting question. We will see later in the semester maybe that it does make sense to talk about factorials of half integers. The factorial of -1/2 is the square root of pi. This is a very important factorial. There's another assumption that we're making. Come in. Well, can someone open the door? Because I don't want to risk with the camera moving. So there's another assumption we're making. What's the other assumption we're making in this problem? We have C cookies, P people. How many ways can we divide? So I would say the other assumption is that all the cookies are given out. Would it be acceptable if I have to divide 10 cookies among 5 students and I give a token cookie to Sean, because Sean is going to be my point for the entire semester now, because that could be anybody, and I keep the other 9 cookies for myself? Can I say, hey, I divided the cookies among the class? This is where it comes down to English and phrasing. How many ways can you divide? I'd like to say all the cookies are being divided, but you could consider the related problem where you divide up to, or you distribute up to C cookies. Okay, so I want to talk about a couple of different ways to program this, and then we'll move on to some other problems. So I'm doing things in Mathematica. As I said, the reason I like Mathematica is because when I went to college, this is what we used for our massive physics labs, so I got to be pretty good at it. I can program in C, Basic, Pascal, Logo, Fortran, most of these languages you may have heard of in history books. They're all essentially the same. The syntax changes. And what I will often do is I will open up a second window so I can just test things in that window. So here is the very first program, and it's a really simple one in Mathematica. You want descriptive names. So the name of this function is C cookies 5 people. num_c, I should really put in a little, says, num_c is the number of cookies to divide among 5 people. And so here you can see the program is hardwired to be dividing among 5 people. There are faster ways of writing what the sum is. I'm just choosing to do the simplest way. Module is Mathematica's way of saying that we have a function. The curly braces here means I have no local variables. Local variables will only be seen by that function and not be seen elsewhere. I'm kind of careless in my Mathematica programming. I often like to have my variables seen when the function ends. And so I'm going to let x be the sum of the sum of the sum of the sum of the sum, so it's a 5-dimensional sum. My variables are going to be a1, a2, a3, a4, a5. I'm going to sum over a5 first, then a4, then a3, then a2, then a1. Each variable goes from 1 to the number of cookies, and I add up how many cookies the first person, second, third, fourth, and fifth get. If that equals the number of cookies, then that was a success. And that's a valid distribution of cookies. If it doesn't, it's a failure, and I put it as 0. And so as I loop through all of this, this will give me how many ways there are to distribute num_c cookies among 5 people. You always have to be careful when you're comparing programs that you're running them on the same system. Let's see now. So it should take around 14.4 seconds. Okay, it's taking about 4 seconds. And the reason is I must have run it earlier when I was on battery saver mode, and now I've put it on balanced mode. So the program is going to be a little bit faster. So we can do it again. It should be around 4.2 seconds. That's not too much time to wait for. Okay, 4.3. This is a horrible code. If I were to double the cookies from 20 to 40, about how much longer do you think it would take this code to run? Yes.
Like 30 times longer.
About 32 times longer. Because I would be doubling the range of the sum, so my number of computations would increase by a factor of 2 to the 5th. So this program is going to be terrible in terms of the size of num cookies. It's going to be growing fast. And so, as long as I'm talking, I'll put in 40, and we can see how long that will go. Well, 32 times 4, you can get a sense of how many minutes that's going to be. This will be on the order of 2 minutes. I don't think I'll be spieling for this on 2 minutes, but we'll see. All right. Let's think about how we could make this code more efficient. And I guess the last thing is at the end, the return x just means output that as the value of the function. I could have done this with just one sum command and then had 5 statements afterward. And you just have to look up in Mathematica the order in which you do things. So over here, if I do question mark and I do sum and then shift enter to compile, shift enter is how you compile things in Mathematica. It can't open it up right now because it's running on the other program, but it will eventually open up a little box that says everything it knows about sum. If you want more information, there'll be a double arrow down here that you just click on. All right, so the program down here is slightly faster. So what you notice now is I only have 4 variables. And I see if the sum of the 4 variables is less than or equal to the number of cookies, I count that as a success. And the reason is if I know how many cookies the first 4 people get, and it's at most the number of cookies, how many cookies does the 5th person get? The remaining. There's no need to do that whole loop for that next person. So we can remove one summation variable. Theoretically, does it matter if we do this with 4 sums or 5 sums? No, not at all. From a practical perspective, however, there is a huge efficiency. So right now, hopefully, we're getting close to that 2-minute warning. Still running a little bit right now. This will save us an enormous amount of time. It's going to kill one whole variable. And if the variable is running up to 20, that's killing a factor of 20. If it's running up to 40, that's killing a factor of 40. Now, in terms of what happens as the number of cookies grows, it's not going to be the greatest. It's going to be a polynomial savings, but it's going to be significant. So I'll run that in a moment. Okay, it finally finished. 120.37 seconds. So the guesstimate of 2 minutes was not that bad. Over here, if we run this now, I'll compile this. If we run this with 20 cookies, it's 0.18 seconds. This should be a factor of 30 longer. So 0.2 times 30, about a second. I've got 2 seconds. Did I make a mistake? Sometimes when it's a really small cal, it's going to have issues. It's around 2.5 seconds, which is much better than 120 seconds. Now, can we do anything even faster? So the next line is an even better way of doing the coding. So again, my only input is going to be the number of cookies. And now I'm going to do a sum on 4 things again. But what I'm going to do now is A4 goes up to num_c minus A1 plus A2 plus A3. What's going on in the previous one is I'm spending far too much time counting configurations that are absurd. Once A1 and A2 add up to something more than the number of cookies, is it worth looking at how many cookies person 3 and 4 get? We know each person gets at most num_c cookies, but once I've already distributed more than num_c cookies, I should stop. So if I spend just a little bit of time coding this, A4 can go from 0 all the way up to num_c minus how many cookies have already been divided. A3 can go all the way up to num_c minus the number of cookies divided. A2 can go from 0 all the way up to num cookies divided, number of cookies distributed. And then A1 can go from 0 to num_c. And what this will do is that we will never be giving out more cookies. And so now if you notice, my sum is just going to be 1, because it's always going to be a success. And so now, let's see what happens if I try to do 40. It was 0.03 seconds to do 40. The other one was about 2.5 seconds. The other one was 120. So for here, I could probably do 400 without too much trouble. And so maybe I'm getting a little bit greedy to do 400. I would have thought it would have finished by now, but yeah, it's not that important. So I'll go to, I think 200 wasn't too bad. So any questions on this basic coding? All right, so 200 was about 6 seconds. And this allows us to investigate significantly further. There is a major problem with what we're doing, is I have hardwired the number of people into the program. And the reason is the number of loops I have to do is going to be a variable based on the number of people. So how would you handle a variable number of variable loops? So there's a lot of different ways to do this. I'm going to show you one way. It is not necessarily the best. We have CS people in the class. If you want to eventually talk to us about better ways of doing this, feel free. I like this way because it allows me to show you some fun mathematics. It allows me to show you some fun coding. It allows me to show you a lot of the functions that Mathematica has predefined. So C cookies P people has 2 inputs, num_c, number of cookies, and num_p, number of people. The underscore means these are variables. The colon equal means I'm defining this to be a function. I'm defining this to be the module that comes on, no local variables. Whenever I code, I always, if I start a begin brace, that means a begin. I always immediately put the other closing brace, the end brace. You should really comment your code, especially when you do things that are non-trivial. So here, num_c is number of cookies, num_p is the number of people. Count is 0. This is going to count the number of successes. And I'm going to not surprisingly start at 0. The key idea is that I can count in binary, or more generally in other bases. I don't have to count in base 10. So what I'm going to do is I'm going to count from 0 to num_c plus 1 to the num_p minus 1 minus 1 in base num_c plus 1. This is not the most efficient way of doing it, but this is not a bad way, and this is a really useful idea for a bunch of things. If I'm dividing cookies among a number of people, let's say I have 10 cookies. The maximum number of cookies someone can get is 10. Well, what I can do is if I write my numbers in base 11, what are the digits in base 11? 0 through 10. So I want to just count in base 11. So that's what the num_c plus 1 is. I'm working in base 1 more than the cookies. And then if I look at the base 11 representation of a number, the first digit is how many cookies the first person gets, the second digit is the number of cookies the second person gets, and so on and so on and so on. This is going to be very similar to these 2 algorithms here. It's going to be somewhat slow. But I can very easily do this, and I can now have the number of people as a variable. And so if the sum is at most num_c, then I can give the remaining cookies to the new person. So integer digits is a wonderful function. It converts n to a list of numbers in a different base. So here I'm using this thing called integer digits. My input is n. Num_c plus 1 is the base. And then the num_p minus 1 means pad the number so that it has a certain number of digits. So if I'm working with 5 people, I want to work with numbers that have 4 digits in their expansion, because the 5th digit will then be forced upon us. Right? Well, when I look at a base expansion, let's say I want to look at the base 11 expansion of 15. What's the base 11 expansion of 15? One 4, right? So the base 15 expansion, the base 11 expansion of 15 is 1 4. But if I have 4 people, I'm supposed to have 4 digits. I really want the number to be 0 0 1 4. So what this padding does over here is it makes sure I have the right number of zeros in the beginning. And now I just go from 0 to num_c plus 1 to the num_p minus 1 minus 1. So that'll be a number that would be 11, 11, 11, 11 if I have 10 cookies and 5 people. I write the number in base 11, padding it with zeros. I sum the digits. So the double brackets means take the ith entry of this list. And I'm going to sum this list from 1 to num_p minus 1. And if it's less than or equal to num_c, it's going to be a success, because I can then just assign the remaining cookies to the last person. And so here's my code. I can now do this for 20 cookies and 5 people. Yes?
I'm just not too sure if I understand why the key idea works. In other words, why does listing the terms in base 11?
Sure. So if you list a number in base 11, so base 11, the digits are 0 to 10.
Yeah.
So I want to count from 0 to a certain number. Basically, I want to count to the number 11 to the 4th minus 1. What's the number right before, I mean, 11 to the 5th, maybe?
Yeah.
I got to be very, no, I think it's 11 to the 4th because the first digit is 11 to the 0, then 11 to the 1, 11 to the 2, 11 to the 3. So if I count to 11 to the 4th minus 1, that number, base 11, that is, 10, 10, 10, 10, base 11. The digits are all 10s. Or if you want, using, Roman numerals, x, 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 base 11. If I added one number to that, base 11, x, 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 x plus 1 is 1, 0, 0, 0, 0. So when I write my numbers in base 11, a general number will be, say, A1, A2, A3, A4, base 11. This is going to be how many cookies the first person gets. And it's going to be a number between 0 and 10. This will be the number the second person gets, and it'll be a number between 0 and 10. Third person, fourth person. And then all I need to do is check and see if the sum of those four numbers is at most 10. If it's at most 10, I've assigned at most 10 cookies. And then I can give the remaining cookies to the fifth person.
Okay. Got it.
Yes?
Can we make that a lot more efficient?
Oh, yes.
By making the upper bound, smaller,
Well, I've got to be careful because I could have the number 10, 0, 0, 0. That's a valid count number.
Right. Can't that be the largest?
But that should probably be the largest. So I think you're absolutely right that we can't go beyond that. And so we could, yes, you're right that we could easily make that larger. That's a very small change to do, but how much is it going to save this in terms of coding? Well, it means it's going to save us maybe like 1 over num c, maybe? Because we're not going to have to do like the last one. Or maybe 1 over num c plus 1. But that would be a very good savings. Absolutely could make it more efficient. Now, this is not the best way to be doing things, because I have a lot of counts that don't matter. The best way is this counting method over here. But the problem is if I want to do a general number of people, I don't necessarily know ahead of time. Now, there are ways to do for loops and sums when you don't know the number of variables ahead of time. I didn't want to go into that coding right now. I want to concentrate on very simple, straightforward things, for loops, if statements, stuff like that. And we'll get to a few more of these. I just want to give you a general sense. So in Mathematica, Shift-Enter compiles a line. This is a simple program. What I'm going to do now, and I guess this is kind of small, I'll make it a little bit larger. For C goes from 1 to 20, I'm going to use one of my faster counters. And I'm going to just count. And it's going to output the number of ways of dividing C cookies among 5 people. And I get 1, 5, 15, 35, 70, 126, 210, 330, 495. How long do I have to fill today? Et cetera, et cetera, et cetera. And then what I did to save time is I actually plugged this into the online encyclopedia of integer sequences. You can put a nice command. You can print a hyperlink in Mathematica, so I could just directly click on this, and it sends me directly right there. And so it says there's only one result that's found. It did enough, we had enough terms that it uniquely specified. And it says it's the binomial coefficient n4. Okay. Now you notice that there seems to be a little bit of a shift. 5 was my first term, but it's 1, 2, 3, 4, 5. It's like the 6th term in the sequence. So you can begin to see how things are shifted. And if I do this for maybe 4 people, 3 people, I can really sniff out what the pattern is. And now that I know that it looks like it's some kind of binomial coefficient choose 4, 4 looks like 5 minus 1. If I were to do this with 6 people, I'd be getting things choose 5. It really suggests what's going on. And the solution is basically putting in partitions. If I have 14 cookies, and Cookie Monster gobbles up 4 out of 14 cookies, how many cookies are left? 10. And so everything up to the first gobbled cookie goes to the first person, everything between the first and the second gobbled cookies goes to the second, and so on and so on and so on. And so there's a one-to-one correspondence with how many ways can Cookie Monster eat 4 cookies from 14 as there are to distribute 10 cookies among 5 people. Okay, so this is really all I want to say on programming the cookie problem. Another thing you could have done is you could have started by saying, look, I want to know how many ways there are to divide 10 cookies among 5 people. Let's do an easier problem. How many people should I assume? 1. All right, how many ways are there to divide C cookies among 1 person? 1, it's the person's lucky day. Now let's say there's 2 cookies. I'm sorry, 2 people. What you might say is, well, however many cookies I give to the first person, the second person has to get the remaining. And so you would see the first person could get 0, 1, 2, all the way up to num cookies plus 1. So there's num cookies plus 1 ways. So you start to get some idea by looking at these low-dimensional cases. What if I have 3 cookies? Well, once I give the first person the number of cookies, now I've reduced it to a lower problem. And now I'm dividing the number of cookies. I can begin to prove this by induction. So you might be able to guess the formula and then prove it by induction. So again, the goal is not to just jump to the solution as the binomial coefficient. It's to think about a thought process that will allow you to handle new problems. And so the idea here is, start small case, p equals 1, p equals 2, see patterns, move up by induction. And then, of course, the OEIS is wonderful. Okay, absolutely wonderful website. Once you have an idea of what the formula is, the induction is a lot easier. It's not cheating to use the OEIS. This is not Tour de France. This is not Major League Baseball. They're not going to test you and see, did you go to this website before you proved your theorem? I once gave a talk to the grad students at Brown when I was a postdoc there on how to use the OEIS to prove theorems. And I said there are a lot of times when I'm doing things in number theory and I can calculate a few terms. And I'm trying to sniff out the pattern. Sometimes you don't have enough terms for the OEIS to be useful, but other times you can. For the chess problem, we can calculate enough terms, the queen and pawn problem, for the OEIS to tell us this is the answer. Unfortunately, the sequence is so hard to do, we don't know enough information as to maybe more than 20 or 40 terms in the sequence. Okay, any other questions on the cookie problem? Okay, the next problem I want to do is a really fun math riddle I got a couple of years ago when I was at one of the top math institutes in the world. And I am surrounded by a lot of the absolute top number theorists of the field. I'm just honored to be in the room and occasionally say things that they care about hearing. And we got the following wonderful problem. So you're given the digits 1, 2, ... 9, form 3 fractions, a over bc. And your bc here means 10b plus c. Okay? So for example, maybe we could have 5 over 34 plus 9 over 81 plus 7 over 26. Okay? So that would be an example. Okay. Use each digit only once. Can the sum equal 1? Okay. We have 9 slots to put in the numbers. Is there a way to put them in so that it will add up to 1? You can start playing some games and say, well, okay, what must be true about the denominators? Maybe the 5 has to be in a good place, or maybe the 9 has to be in a good place. And you can start trying to prove lemmas. Or, what else could you do? Yes? Put it in a computer. How efficiently do we need to write the code for this? Why 6 factorial? Well, how many options do we have? How many fractions do we need to consider?
Yes, it's 3 fractions.
Well, it's 3 fractions. So a lot of it comes down to how cleverly do you want to program. If we do it naively, because it does matter if you're in the numerator or the denominator. How many ways are there to throw in these 9 numbers into these 9 slots? 9 factorial. All right, so let's look at 9 factorial. So here, finally, here's the sum function. If I click on this, it will open up yet another window, and it starts telling you how to do sums, how to do multiple sums if you want. And in this multiple sum, it does ij, it does the j sum first, then the I sum. It starts on the outside and moves in. All right. Well, what we can do is we can calculate what's 9 factorial. So 9 factorial is 362,000. It's not horrible for a computer. And I only need to write the code once. Now, by symmetry, I can actually do a little bit of a savings. I could save a factor of 6, because it doesn't matter the order in which I write the 3 fractions. The problem is, how do I code that symmetry? I might actually spend more time figuring out how to code that symmetry than I will save in running the program. How many times am I running this program? Once. This is not something I'm doing repeatedly. If it's something I'm doing repeatedly, do I care about efficiencies? Absolutely. If it's something I'm doing once and only once, I can afford to be inefficient. I would rather spend less time programming and more time running if the total sum is smaller than more time programming and less time running. So one thing is to just get a little bit of a sense of how things go in Mathematica. So, what I'm going to do here, I could have written a little for loop to add the numbers one at a time to the list. I'll just type it in because it's so fast. But if you wanted to, you could also do list is empty for j equals 1, j less than equal to 9, j plus plus, list equals append to list j. And then I can print list. Oops. And then it prints out the list. Okay. So now I want to choose a permutation of the list. Well, one thing I can do is I can choose a number from 1 to 9, pull that number out, delete that number from the list, choose a number from 1 to 8, choose a number from 1 to 7. So I can do this with maybe 9 sums, 9 loops like this. Or what I can say, are people able to see it on this size, or let me make it larger? So you can start typing things. Ooh, there's something called random sample. I wonder what that is. Okay, I actually don't wonder. I actually know what that is. So I put a question mark in front of this to see what this is. Random sample gives us, okay, let's see. Oh, random sample gives a pseudo-random permutation of the EI. So do I want a pseudo-random sample? All right, so there's something called permutations down here. Let me click on permutations. And so again, you can navigate the help menus very well. It's dynamic. You can click. You can keep moving. I've done this before. I know it's permutations, not random sample. Random sample is clearly not what I want to do for this because I want to go through everything. If I want to estimate something, if I want to do some kind of Monte Carlo simulation, random sample would be fine. I want every sample. So I want a permutation. Generates a list of all possible permutations of the elements. Hey, that's what I want. Permutation lists gives all permutations containing at most n elements. Permutation gives, with the curly braces, gives all permutations containing exactly n elements. So I want permutations. So what I'll do here is I'll go permutations of list. Now, Now what it's showing here is that there is a huge number of permutations and it's not going to be able to display all of them. And it's assuming I do not want to display 362,000 yada yada yada. If I want to, I could hit show more. That's probably a stupid thing to do. All right. But it's not going to show everything. It's showing a few more over here. it's treating me like a, now if I put a colon at the end, that means suppress the output. But what you should be able to see is that it actually generated the list very quickly. And now what I can do is I will give it a name, perm list. Try to have good descriptive names. And then now what I can do is perm list 3. That will give me the third element of the permutation list. And what you'll see is it's 1, 2, 3, 4, 5, 6, 8, 7, 9. The second one is probably 7. Actually, good. It's interesting as to how is it choosing the. So it's 7, 9. So it's going to go through all the different ones like this. So what I can do is I can take my permutation and I can pull out various things. So I can write some code. So over here, all right, code to look at fractions from 1 through 9, each digit once. Okay. So now we need a name for the program. Fraction check. What are my variables for fraction check? Yeah.
Each element of your perm list.
What's the variable that I'm going to want to pass in when I write this program? I don't need one, right? I'm doing this once. There's no input, right? I'm just going to check things. So list, we'll use the code from here. Okay. Now we'll go, we have our perm list over here, right? And now for n equals 1, n less than equal to 9 factorial, n plus plus. Now, the curly brace means I'm beginning my for loop, and this curly brace here means I'm ending it, and then the bracket is just completing this off. So the curly braces are because I'm going to have multiple statements. So temp list is going to be perm list n. Okay? So I'm going to read in my n factorial permutations one at a time. And now I have to form my 3 fractions. Okay? So now the only problem with temp list is that's a really long thing to keep writing. So rather than writing temp list, I'm going to just write x, because it's faster to write. So now I'm going to do if x1 divided by 10x2 plus x3, that's the first term, plus x4 divided by 10x5 plus x6. And you see how this is in a different color? What do you think that means? Unmatched. So here I have 1 brace on the left and 2 on the right. I need 2 braces for referring to things. So the color coding is wonderful. If I wanted to, I could put these terms here in parentheses, but the laws of my dear Aunt Sally, or please excuse my dear Aunt Sally or Sarah, tell me I will do the divisions like this, and I will combine these, so I don't have to really worry. But you know what? It's probably not a bad idea to just put in an extra parenthesis. It makes it a little bit harder to read, but really worth it. And now I'll do x. Now what I really should have done is I should have done something like this. And then down here, I would have 2. I would have x, 10 times x. I don't need a multiplication if they're right next to each other, plus x. And the reason is, I would then just paste this 3 times, and I would go here 1, 2, 3, 4, 5, 6, 7, 8, 9. That would just help me type it a little bit faster. And I'll just go 7, 8, 9. Okay? So what I'm going to do now is if this equals 1, so in Mathematica, the double equal signs is what you need for 1. I hate how it keeps changing the font size. So if this equals 1, I have a success, right? And so what I'll do is I will print x. And then, so it looks like I have a brace missing somewhere. So does anybody see where the missing?
The third brace behind X.
Oh, is there a third brace behind an x? Okay. Okay. So you can see it printed it out extremely fast. There was really no point in making things efficient. Now what's fascinating here is we actually have a list with potentially 360,000 elements in it. So I'm not quite sure how Mathematica is storing it. The longer your list is, the harder it is to work with it, the cost it's going to be to cull elements from it. Marching down might not be too bad. This is really getting into some system architecture. But you can see this ran so quickly that it wasn't worth writing better code. The other thing is, are you surprised at the number of answers? Okay, why aren't you surprised? Yes? Yeah, it should be a multiple of 6, because we should be able to move the fractions around, and it seems unlikely that maybe, you can't have 2 of the fractions, because the numbers have to be distinct, so it should be a multiple of 6. So there turns out to be one and only one solution. We could try to generalize this problem. How might you generalize this problem? Yes?
Like raw bases.
Yeah. Generalize to another base. So base 10, we have 9 non-zero digits. We had 3 fractions with 3 digits. What might you choose now for generalization? What would be the next base you might want to try? There's lots of ways you can go. Do you think we should always have fractions with one numerator, with one element for the numerator and 2 elements for the denominator? Do you think maybe we should have 2 elements for the numerator, 2 elements for the denominator? Maybe 2 elements for the numerator, 3 for the denominator. Maybe, base 16 or 17 could be something interesting. Maybe we'd want to go up to 4 fractions. So, I pose this as a problem. I'll make this extra credit. Find a generalization with a solution. Maybe it's not 1. Maybe it's another nice value. 1 just happens to be a fun value. When you think, what are your good numbers in mathematics? 0, 1, square root of 2, e, pi. You see anything like this, you're happy. Do you think you can always generalize to another base and have the sum be rational? Yeah, that's not that hard because it's always going to be rational because they're fractions, right? So you would have to want to have some kind of interesting number. So potentially maybe 1/2 is an interesting rational number, but the fact that it's an integer, the integer is a very nice special type of number. All right, we've got a few minutes left. Is there any problem people are particularly interested in seeing? Okay.
That was, I think, you have a set of n,
Of n.
and
So is this like 1 through n?
n distinct elements,
Okay.
and then you take any subset and make that a of n, and then you take a subset of a and n, which is b of n, or maybe b of a, whatever, it doesn't really matter. And then the question is, how many ways can we do this?
Or can you do this? So for each subset A, we then form a new subset. And it's possible to have it as an empty subset, right?
Yeah, I think so.
Okay.
That whether or not you count the fringe elements doesn't really matter.
Okay. So now, when you look at B of A of n, I could get the same subset B of A of n multiple ways.
Right.
But we count them as different because
Right.
they went through different A's. Okay. So do you know the answer for how many ways there are? Okay. So how many ways are there to choose a subset from n elements? Right. So there are 2 to the n subsets of n elements. Right? So now what we want to do is for each subset, the number of elements it has is going to be a function of its size. If A of n has k elements, how many B of n do we have? 2 to the k choices for B to the n, or B of A of n. How many subsets of the n elements are of size k? And choose k. And choose k. So we would want something like the sum, k goes from 0 to n. It's n choose k, and then it's 2 to the k?
Yeah. That's what I was thinking.
Okay.
I was also told that it has a nice neat answer,
Yes.
but I'm sure we could do some sort of manipulation to make that.
Yes. No, there's a one-line answer from this point. Okay. I'm just changing the margin so I can just have it all in one line. Okay. So now, what I can do is I can write this as 2 to the k. Oops, I don't want that. Okay, 2 to the k is 2 to the k times 1 to the n minus k. I'm multiplying by 1. The two most useful techniques in mathematics are to multiply by 1 and to add 0. And one of my professors at Yale said the log of 1 is 0. So there's really only one thing you can do in mathematics. You can do nothing. The goal is to do nothing well. This is the binomial theorem. Because now what I can do is I can write this as, the sum on k, n choose k, x to the k, y to the n minus k. So by the binomial theorem, how many of you have seen the binomial theorem? Have you seen the binomial theorem? So this is just going to be x plus y to the n. So for us, we would get 3 to the n. Okay, so let's check. So we would want to write some code. So subset problem. Okay, so now we want to know how many ways we can do this. So what we want to do now is we want to have a function, subset function. And the input is going to be, and I can't use a capital N because for Mathematica, the capital N is reserved for taking numerical values of things. So you have to just be very careful sometimes as to what you're using. So what I want to do now is I'll form a function, and then I immediately end things. Okay, so what I want to do is I want to keep track of things. So maybe, I set count to be 0. And now I want to go through all the permutations. So list is going to be empty. And then for j equals 1, j less than equal to n, j plus plus, list equals append to list j. And now what I want to do is I want to look at all the permutations of the list. Right? So perm list would be permutations of j. Right? Not of j, of list. Right? And then maybe for m equals 1, m less than equal to the length of perm list, although we know what that is, that would just be what? Oh, wait a minute, we've got to be careful here. This is looking at all the permutations. We don't necessarily want to take all the permutations, we want to take all the subsets. And so it would be permutations, and then here it would be all subsets of size at most n. Now the problem is this may not include the empty set. So we could come over here and do permutations of list. All right, so I'm going to make list a little bit shorter right now. So now if I go permutations 2, it does include the empty set. But this is why you always just do a quick check like this. So now when I come back over here, m goes from 1 to the length of the perm list in steps of size 1. n plus plus means in steps of size 1. And now what I want to do is count is going to be count plus I want the number of subsets of the permutation of what I choose, right? So the element I'm going to choose is perm list m, right? And I want to know how many subsets this has. So the question is, do I know that this is just 2 to the length of that? If not, what I would have to do is take the number of permutations of that and count that as well. So we'll assume we know that the number of permutations is just the length of this. We're fine with using that in the interest of time. So it'd be 2 to that.
Why did we put 4m?
So I go through all the possible permutations for my initial list. And for each one, I increase the count by this. And I'm going to print count. So subset function of 3. So I don't think I've ever used n as a... Oh, so it says I'm changing n somewhere. Oh, this is, I said, this should be an m plus plus, not an n plus plus. Okay. All right, so let's see if this works. So I got 79. And what should we have gotten? 81. So the question is, are we missing a few things? I got 13 for 2. So there's a small error in the code here. So j goes from 1, j less than equal to n, list is append to list of j. Let's look at the length of list, of prom list. So this says the length is 5 when we have 2. It should really be 8. And so when we did things over here, we had permutations list 2. Oh, wait, this was only giving us 5 things. 1, 2, 3, 4, 5. How many things should there have been?
You're still doing permutations.
We're doing permutations.
So
We should be doing subsets. Because here it's, 1, 2 is different than 2, 1. And that's where the error is coming from. So I'm using the wrong command here. So we just have to put in the right command. So it's time to solve the class, unfortunately. So I will fix that code for the posting. But this is the general structure of how you would do that. And then you would snip out the pattern 3 at the end. And if I had done the right thing, it would have been a very wonderful, dramatic ending to the lecture.